Good morning. So, we are going to continue our discussion on neural network for pattern recognition. So, firstly I will just briefly go through what we have done in our last class, then we will proceed further. So, in the last class we have talked about a single layer, single output neural network, where when I say it is single layer, basically there are two layers. One of the layer is the input layer, and the nodes in the input layer are simply used to connect the feature vectors. So, the purpose of this input layer node is whatever is inputted to the input layer nodes, those nodes simply forward that input to the layer above it, okay. And those inputs get weighted by the corresponding connection weights connecting the input layers to the layer above it and summed up at the next layer, and on top of that you apply some sort of non-linearity. So, effectively the single layer, single output neural network we have said was something like this, that it has a number of input layer nodes. So, this is the layer which is input layer. So, the number of nodes in the input layer is same as the dimensionality of the feature vectors plus 1, which is used to take care of the bias or the bias weight, okay. And the number of nodes in the output layer in this case will be only 1, which will indicate either one of the two classes, okay. So, if the output of the output layer node is greater than threshold, in which case the output of the output layer node will be set to equal to 1, which will indicate say class 1, and if the output is 0, it will indicate class 2. So, the connections that we will have is something like this. So, here I have x 0, which is usually set to 1, and the connection weight over here is W 0, which takes care of the bias weight. Whereas, the other inputs will have the different feature components x 1, x 2 up to say x n, and the corresponding connection weights are W 1, W 2 up to W n, okay. And output of the output layer node, which let us say that this output is equal to D, okay. So, this is my output layer node, okay, where D will be equal to the weighted sum of the input feature vector components. So, it will be simply summation of W I x I, where I varies from 0 to n, okay, where n is the dimensionality of the feature vector and x 0, which is usually set to 1, that is to take care of the bias weight, okay. So, then what we said is, while training the neural network, we have to decide these connection weights, or what will be the weight vector that will classify the unknown feature vectors between one of the two classes, say class omega 1 and class omega 2. Okay. Now, while training, because all the feature vectors which are given, we know what is the class belongingness of those feature vectors. So, we effectively know that what is the expected output. Okay. So, if I take a training sample, a training feature vector, which we know that the training feature vector belongs to class omega 1, we know that the corresponding output has to be equal to 1. Or if I know that the feature vector belongs to class omega 2, then it is known that the corresponding output has to be equal to 0. So, for the training samples, for each of the sample which is presented to the neural network, we know what is the corresponding output. Okay. And because initially the weights are not set properly, because we start with arbitrarily set weights of very low values. So, even if our training sample which belongs to class omega 1 is given to the neural network, the output may be 0 or output may have any of the continuous values between 0 and 1. Okay. So, it may not be equal to 1. So, what is the expected output and what is the actual output that you get, the difference between between these two is the error. Okay. So, if I say that my actual output that I obtain after giving a training sample, after inputting a training sample is given by the expected output is say D, and the actual output that I get D, capital D, which is nothing but this summation W I x I varying from 0 to n. Okay. Then the difference between these two, using the difference between these two, I can define what is the error. Okay. So, if I define the squared error, the squared error is given by E is equal to half of D, which is the actual output, minus the expected output, or which is also called target output. So, capital D minus D whole square, this is my squared error. So, while training the neural network, the aim is that we should be able to set the weight vectors or the connection weights in such a way that this sum of squared error will be minimized. Okay. So, for that again we can make use of the gradient descent procedure. So, for making use of the gradient descent procedure, we have to find out what is the gradient of the error with respect to the weight vectors. So, that means what I have to find out is del E upon del W I for a particular weight vector. And if I compute this term, you find that this is nothing but, if I take the derivative of this with respect to W I, okay, this will be simply D capital D minus D into del capital D minus D upon del W I. So, it is capital D minus D into del W I of capital D minus lowercase d. Okay. So, if I just concentrate on this particular term, because there was question on how do we get this. So, if I concentrate on this particular term, okay, here you find that this lowercase d. So, what I am trying to find out now is what is del W I of capital D minus lowercase d. Okay. So, as I said that this lowercase d, this is our expected output or target output. So, that is fixed. Given an unknown sample, given a training sample, as I know what is the class belongingness of that training sample, so my target output is fixed, which does not depend upon W I. Okay. So, this derivative del W I into capital D minus lowercase d, this is nothing but del W I of capital D, because lowercase d is independent of W I, and this capital D is nothing but summation of W I x I, okay, where I varies from 0 to capital N. Is that okay? So, you find that if I take the derivative of this summation with respect to W I, then only term that remains is nothing but x I, because all other terms are independent of W I. Only W I times x I, that is dependent on W I, and if I take the derivative, it simply becomes x I. Okay. So, that is why this del E del W I that we have obtained as capital D minus lowercase d into x I. Okay. So, only the simple derivative expression this has given me this particular expression. Okay. So, while training the neural network, as our aim is to set the weight vectors, okay, so we have to go for an weight adjustment algorithm. That is what is neural network training. So, in this weight adjustment algorithm, initially we have to start with some arbitrary weight vectors. Okay. So, you set some random weight vectors for different wi, you select some random values and the values are quite small. Okay. So, you generate small random values which are taken as wi, or I generate a random weight vector. So, I have that wi 0, that is the initial weight vector, which is set randomly, random but very small value, and then in every iteration wi k plus 1 will be some update on wi k, that was the value of wi in the previous iteration. Okay. So, this will be wi k minus eta, where eta represents what is the rate of convergence, into this expression del E del wi, which is nothing but capital D minus lowercase d into xi. Okay. So, this will simply be capital D minus lowercase d into xi. This is my update rule. Okay. So, how do you train the neural network? You feed the training vectors one after another. For every such training vector, you find out what is this component d minus capital D into xi, which is the input vector component. Okay. And this wi k was the previous weight. So, you modify the previous weight according to this update formula. Okay. So, that you do in the first pass for every sample. With every sample, the weight will be modified. Okay. So, once the weight is modified for every sample, I do not know whether for a previous sample for which the weight was modified, because after modification with the previous unclassified sample, again the weight vectors are getting modified. So, it may so happen the previous sample, with the previous sample, either the previous sample will be properly classified or it will be wrongly classified. So, if it is wrongly classified, I have to modify the weight vector again, and this iteration is continued until and unless either all the training vectors are properly classified, or I come to a situation where the error, that is d minus capital D minus lowercase d, that error is quite small, it is within tolerable limit. Okay. So, the convergence criteria or the termination criteria of this iterative algorithm will be that either in a complete pass all the training samples are properly classified, or I get an error where the error is very small, the error that I can tolerate. Okay. So, that will be my termination criteria or convergence criteria for this training algorithm. Okay. So, with this single layer single output neural network, we have considered only two class problem, that is if the output is greater than threshold or if the output is greater than 0, I say that the sample belongs to one class. If the output is less than 0, I say that the sample belongs to another class. So, the kind of thresholding that we are applying is a hard threshold. Okay. But when we have multi-class problems, naturally the multi-class problem cannot be taken care of by a single output. So, I have to have multiple number of outputs. So, that gives you multiple output single layer neural network. Okay. And the action of this will be similar to our linear machine. In case of linear machine, we have said that for every class omega I have a discriminant function g I of x. Okay. And we said that if g I of x is greater than g j of x for all j not equal to I. Okay. So, this indicates that the feature vector x belongs to class omega I. That means, for every class I have a discriminant function. For the given unknown feature vector x, you compute the discriminant function for every class, and whichever class gives you the maximum value of the discriminant function, okay, you assign this unknown feature vector x to the corresponding class. Right. So, if I want to have this similar kind of action using this neural network, then obviously I have to have a neural network with multiple number of outputs. Okay. So, the input layer as before will remain same, that is the number of neurons in the input layer will be same as the dimensionality of the feature vectors plus 1. So, that additional node takes care of the bias weight. Okay. And in the output layer, we have a number of nodes which is equal to the number of classes that we have. Okay. So, if there are say m number of classes, then in the output layer I have to have m number of nodes. Okay. And here I have n plus 1 number of nodes, where n is the dimensionality of the feature vectors. Okay. So, you apply the feature vectors to this input layer nodes. As we have assumed, the first component is equal to 1, okay. That takes care of the bias weight W 0. Other components are x 1, x 2, so up to here I have x I, okay, and here it is x n. Now, the connection is like this, that for every input layer node, the output of every input layer node will be connected to the input of every node in the upper layer. Okay. So, the connection will be like this. Let us consider one node over here. So, this is the jth node. Okay. So, similarly, it will be like this. So, similarly, this will also be connected to every node in the output layer. Okay. And these are the outputs from every output layer node. Okay. Now, output of the jth node, suppose I call it jth node in the output layer. Output of the jth node in the output layer will be nothing but, if I represent this by say dj, which will be equal to sum of wij x I, where I varies from 0 to capital N. Okay. And what is wij? wij is the connection weight from the output of the ith layer in the input node to the input of the jth layer in the output node. So, when this is my ith node in the input layer and this is the jth node in the output layer, this connection weight from the ith node in the input layer to the jth node in the output layer is wij, right. So, given this sort of connection and this sort of network topology, here training of the neural network means that I have to select all the connection weights wij for all values of I and all values of j. Okay. And unlike in case of single layer network, single output neuron, where the output was a scalar value, it was not a vector. Okay. It is a single value, either 0 or 1. In case of multiple output, the output will not be a scalar, but the output will be a vector, because I have capital M number of components. All the output layer nodes will give me some output. So, that means output is also a vector, it is not a scalar. However, for a known feature vector, that is during training, as we are using all the feature vectors for which the class belonging randomness is known. So, if I know that a feature vector belongs to class say 3, class omega 3, I know my target output should be only the third neuron in the output layer should give me a value 1, all other neurons in the output layer should give me value 0. Okay. If the feature vector belongs to class omega 1, then only the first output layer neuron should give me an output 1, all other output layer neurons should give me a value 0, right. So, my target feature vectors will have only one of the components to be equal to 1, the rest of the components are all equal to 0. That is my target. However, as initially the weight vectors are not properly said, I may get an output vector which is not same as target vector. Okay. So, accordingly the error that I get is a vector difference, the difference between two vectors, the target vector and the actual vector. Is it okay? So, accordingly we have to define the sum of squared error, which in this case we can define as E is equal to half of dj minus log s dj. So, this dj means this one, the actual output of the jth neuron in the output layer node, in the output layer. Okay. Whereas, this log s dj, this indicates that what should be the value of the output of the jth neuron in the output layer in my target vector. Okay. And because I have m number of components in the output vectors, so the sum of squared error will be simply this square, take the summation for j is equal to 1 to m, as I have m number of components in the output vector. Okay. Now, given this, here again you find that for the training algorithm or for learning of the neural network, I have to take the gradient of this with respect to wij. Okay. Again, following the similar derivative procedure, I can find out that this del E del wij will be simply dj minus dj into xi, where xi is the ith component of the input feature vector. Okay. I will get the same, following the same procedure, I will obtain this. So, once I get this, now my training algorithm as before will be wij 0, that is the initial weight, you have to set arbitrarily or this will be random, but a small value, and while iteration this wij k plus 1 will be equal to wij k minus eta, which is nothing but our rate of convergence. This decides rate of convergence into dj minus dj, which is the error, times xi. Okay. So, this is what is the training algorithm. Okay. So, as before, the training algorithm being an iterative procedure, I have to decide what is the convergence criteria. So, again here the convergence criteria can be either all the training samples are correctly classified by a particular set of weight vectors, or I reach a condition where the error value is very small, that is the error is tolerable. Okay. Now, if you look at the discriminant functions that this kind of neural network actually imitates, this is a linear discriminant function, because it is nothing but sum of wij xj for all values of I varying from 0 to capital N. So, it is a linear equation for fixed weight vectors. That means, every neuron in the output layer node actually gives me the linear equation of a state line, or the equation of a hyperplane. So, that simply says that if the classes are linearly separable, I can design the decision boundary using this sort of neural network. Okay. But if they are not linearly separable, a single layer neural network cannot give me the decision boundary. Okay. So, let us take some few examples from say binary arithmetic. Let us take the case of an AND gate. So, all of you know that AND gate, the truth table of an AND gate. If I have two variables x 1, x 2, and I have this output y, the truth table of the AND gate is simply 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 1. Okay. I can consider these to be a two-dimensional binary feature vector, okay, x 1, x 2 to be two-dimensional binary feature vectors, which can assume one of these four different values. Okay. And I want to design a neural network which will give me the function of an AND gate. That means, output should be equal to 1 only when both the feature vectors, both the feature components are equal to 1, and output should be 0 if any or both of the input feature components are equal to 0. Okay. So, if I plot it in the form of a graph, so something like this. This is my x 1 dimension, this is my x 2 dimension, and this is the origin. Okay. So, for 0 0, I take 0 over here, this is say 0, and somewhere over here say it is 1. Okay. So, if x 1 is 0, x 2 is 0, output should be equal to 0. Okay. If x 1 is 0, x 2 is 1, then also output should be equal to 0. If x 1 is 1, x 2 is 0, then also output should be equal to 0. If x 1 is x 1, x 2, both of them are 1, then output should be equal to 1. Okay. Something like this. Is it okay? So, find that given this sort of plots of the outputs, I can define a boundary line somewhere over here. Okay. So, this is my classifier, right, and given this sort of classifier, you find that I can have a single layer single output neural network which will give me this sort of decision boundary, and one of the possible neural networks that can give me this sort of boundary is like this. I will have 3 inputs, okay, and 1 output. So, one of these 3 inputs will have input is equal to 1, and the other output inputs will have my feature components x 1 and x 2, right. The connection weights can be something like this. I put minus 1.5 here, 1 here, and 1 here, and this is my output y, right. So, you find that this y actually gives me the equation of a state line, which is nothing but x 1 plus x 2 minus 1.5, right. So, here you find that if any of the components or both of the components are 0, if both the components are 0, output is minus 1.5. If any of the components is 0, the other one is 1, the output is minus 0.5. So, in all these 3 cases, the output is less than 0. Whereas, if both these components are 1, then output is 0.5, which is greater than 0. Okay. So, whenever this y is less than 0, I can set output to be equal to 1. whenever y is less than 0, I can set output to be equal to 0. Whenever y is greater than 0, I can set output to be equal to 1. Okay. So, this simple neural network can perform the function of an AND gate. Okay. Similarly, if I take another example, that is an OR gate. Okay. In case of an OR gate, the similar plots will be something like this. This is x1, this is x2. I put 0 here, 0 here, 1 somewhere over here, 1 somewhere over here. So, in case of OR gate, you find that only when both the inputs are 0, the output is 0. If any of the input is 1 or both the inputs are 1s, in that case output is 1. So, I will have 1 here, I will have 1 here, and I will have 1 here. Okay. Again, in this case, I can define a straight line which will separate between these two regions. Okay. And again, a simple neural network like this with 3 input layer nodes and 1 output layer node. Okay. Where this y again gives me a linear equation which is nothing but x1 plus x2 minus 0.5. Okay. So, here you find that if both x1 and x2, both of them are zeros, the output is minus 5, which is less than 0. In all other cases, if any or both of them becomes 1, the output becomes greater than 0. Okay. So, following the same logic, if the output is greater than 0, I put it to 1. If the output is less than 0, I put it to 0. Then you find that this particular neural network will give me an OR function. Okay. Now, if I take another gate of similar nature, that is XOR gate. In case of XOR gate, if I plot similar functions x1, x2, I put 0 here, 0 here, 1 here, and say 1 here. In case of XOR gate, if the inputs are 0, 0, the output is 0. If the inputs are 1, 1, then also output is 0. If the inputs are 0, 1 or 1, 0, then only output is 1. So, I will have an 1 here, I will have an 1 here. Now, given this sort of situation, you find that I cannot draw a single straight line which will separate the space where in one of the half space the output is 0, in the other half space the output is 1. Or effectively what I need is I have to define 2 straight lines over here. Okay. So, that I can put this 0 output in one region and the output 1 to be in another region. Okay. So, this is a very simple example, and I cannot have the equation of a single straight line which can divide this space into such a sort of region. Okay. So, naturally a single layer neural network cannot give me a solution for a simple problem something like this, where the region cannot be divided into 2 half spaces using a linear straight line. So, exactly for this kind of situation where the region is not linearly separable, I have to go for multi-layer neural network. The single layer neural network does not work in this type of cases. Okay. So, I have to have multiple layer neural network where one of the layer is obviously the input layer, which we do not consider in deciding the number of layers, and the other layer is the output layer In case of single layer, we have said we have only the output layer. Okay. And in between, I have to have a number of hidden layers. Okay. And it is observed that if you have two hidden layers, one or two hidden layers, two at the most, that is sufficient to solve most of the practical problems. Okay. So, you go for multi-layer neural network with one output layer and two hidden layers, or if the problem is simpler, we can have one output layer and one hidden layer. The number of nodes in the input layer will be same as the dimensionality of the feature vector plus 1. The number of nodes in the output layer will be same as the number of classes for which we are designing the classifier, and number of nodes in the hidden layers, those are actually variable. Okay. And so far there is no formal way in which we can decide that how many nodes in the hidden layer that we have to have for a kind of problem. Okay. So, it depends upon how complex the decision boundaries are among the different classes. Okay. So, in case of this multi-layer neural network, which is also called multi-layer perceptron or MLP. Okay. This is multi-layer perceptron. Okay. We have obviously one layer which is input layer, we have one layer which is the output layer, okay, and we have either one or two hidden layers like this. Okay. So, this is my input layer, this is the output layer, and these two are the hidden layer. Okay. So, as before, the outputs from the kth layer goes to the inputs of the k plus first layer, okay, and every neuron, output of every neuron in the kth layer is connected to the input of every layer in the k plus first layer. Okay. So, I put it like this. Similarly, over here, so all of them will be connected. Okay. Similarly, here, and finally, you get the output from the output layer nodes. Is that okay? So, when I consider any layers a kth layer, now find that the number of weight vectors that we have is much more than the number of weight vectors that we had in earlier cases, because from the nodes of every layer to the nodes of the upper layer, I have set up weight vectors, and the number of weight vectors. So, the sets of weight vectors that you have depends upon how many layers you have within this neural network. Okay. So, if I consider say node and not only that, each of the nodes in all the layers except the input layer gives a nonlinear function, employs a nonlinear function, which earlier case we said that this nonlinearity was hard nonlinearity or threshold nonlinearity. That means, over there our nonlinear function in these cases was something like this. The nonlinear function that we had was of this form, that is, if y is less than 0, then output is 0. if y is greater than 0, then output is 1. Okay. So, this is my 0 line and this is y and this is the output. So, this was also a nonlinear function, but this nonlinearity was a hard nonlinearity. Okay. Whereas, in case of multi-layer neural network, the nonlinearity which is used is not a hard nonlinearity, but it is a sort of sigmoidal function. Okay. And the sigmoidal function is given by this expression. So, if S is the argument, then R S, which is a sigmoidal function, is 1 upon 1 plus e to the power minus S. Okay. And if you plot this R S versus S, this is the S and this is R S. Okay. The plot will be like this. Okay. Where you find that when S tends to minus infinity, R S tends to be 0. Okay, because as S tends to minus infinity, this e to the power minus S, that tends to be infinity. So, 1 upon this term tends to be 0. Similarly, as S tends to plus infinity, then this R S tends to be equal to 1. Okay. So, I have the output function which is limited between 0 and 1. As S tends to minus infinity, R S tends to be 0. As S tends to plus infinity, R S tends to be 1, and at S equal to 0, the value of R S is equal to half. So, it is a symmetrical nonlinear function around the value S equal to 0, right. The advantage that we get by using this type of nonlinearity is that this function is differentiable. In case of hard nonlinearity, because I have a discontinuity at S equal to 0, it is not differentiable. Whereas, this function being a continuous function, it is differentiable, and not only that, if I take the differentiation of R S del R S del S, that gives us a very simple form. This is nothing but R S into 1 minus R S. If you differentiate this R S with respect to S, you will get this sort of differential output, right. So, here I assume that in this multi-layer neural network, I have total k plus 1, capital K plus 1 number of layers. One of them is the input layer, and I have capital K number of layers, including the hidden layers and the output layer. So, the total number of layers is capital K plus 1. Okay. And when we say that it is k layer MLP, where k indicates the number of layers excluding the input layer. Okay. Now, given this sort of situation, I have to, when I talk about the input to a particular node or when I talk about output from a particular node, I also have to identify that which layer it is. Okay. So, I have to identify which layer and at the same time which neuron in that particular layer. Okay. So, if I say the output of the kth layer neuron or say ith node in the kth layer neuron, that will be represented by x I k. Okay. This is output of ith neuron in kth layer. Let me put it as lowercase k, so that it is a variable, and we have said that capital K is the number of layers. Okay. So, x I k as k superscript and I subscript, this represents output of ith neuron in the kth layer, and obviously this output is fed as an input to a node in the k plus first layer. Okay. So, when I talk about the output of the k plus first layer or jth output of the jth neuron in the k plus first layer, okay, that I can write as x j k plus 1. Okay. This is output of the jth neuron in the k plus first layer, which gets input, this sort of input for different values of I. Okay. So, this I can write as w I j, because every ith node in the kth layer, from every ith node in the kth layer, this jth node in the k plus first layer gets input. So, this is w I j, and between which two layers. So, I write it as k plus 1, indicating that it is the connection weight between the kth layer neuron and the k plus first layer neuron. So, w I j k plus 1 into x I k, that is output of ith node in the kth layer neuron. Okay. Take the summation of this for I varying from 0 to, let us put it as m k, indicating I have m k number of nodes in the kth layer. Okay. And I is equal to 0 indicates that if I want to incorporate any bias in the kth layer also. Okay. So, I can have bias only in the input layer, I can also have bias in every other layer as well. Okay. So, m k is the number of nodes in the input layer and plus 1. Okay. So, the total number of nodes in the input layer is m k plus 1. So, I set I is equal to 0 to m k. Okay. And on top of this, I have to have this non-linearity. Okay. So, the whole thing will be a non-linear function of this. So, R of this. Okay. So, output of the jth neuron in the k plus first layer is the weighted sum or nonlinear function of the weighted sum of outputs of all the neurons in the kth layer, where this weight is given by the corresponding connection weights w I j k plus 1. Okay. And this is valid for all the hidden layer nodes and the output layer node. Okay. So, every node in every layer gets outputs from the nodes in the previous layer, except the input layer node. To the input layer node, we directly feed the inputs, and the output of the output layer node, that we directly get as outputs, that is not fed to the neurons of any other layer. Okay. So, given this sort of formulation or this sort of architecture of the multi-layer neural network, here again I have to find out what will be my training procedure. Okay. So, to do the training procedure, I follow the similar type of approach, that is the gradient descent approach. So, for that I have to find out what is the error I get at the outputs of every layer. Okay. So, finally, when I am saying that capital K indicates my output layer, let us see what is the error at the output layer that I have. This function R every neuron except the input layer. In input layer it is unity, just linear, whatever is the input you pass it to the output. But in all other layers this non-linearity is present. Okay. Which in case of single layer neuron we said that this non-linearity is present only in the output layer nodes, not in the input layer nodes, and there we have considered the non-linearity to be a hard threshold. Okay. Here we are considering this non-linearity to be a sigmoidal function, it is not a hard threshold. There is reason for it. No, that is what I am saying. We will come to realize that why this non-linearity we are putting. We can do it definitely, okay, because that is also linear. But the problem over there is, if you do not put any such limit, then your network may become saturated. Okay. So, that is why you put the limit at FD neuron. Okay. And we are not putting the hard threshold, but we are putting this continuous non-linearity. The reason will be obvious when we talk about the training algorithms. Okay. Yeah.
So, number of nodes in hidden layers vary from layer to layer.
May vary from layer to layer.
So, any means what factors it has?
That is what I said. There is no analytical approach to find out what is how many number of layers you need or how many nodes in every hidden layer you need. There is no such analytical factor.
Analytical means if we increase the number, the quality of our output.
Up to some level, the quality of output will increase. Beyond that, the quality of output may even fall. Okay.
So this nonlinear function is different for different layers?
It can be different for different layers, or it can be same as well. The usual practice is you use the same nonlinear function. Okay. What is needed is, in each of these layers, the nonlinearity that you introduce, the nonlinearity should be a continuous function, or it should be a derivable function. I should be able to find out its derivative. Its derivative should exist. Okay. That is the constant. Why? As I said, that will be clear when I talk about the training algorithms. Why we want that this function should be a differentiable function. Okay. So, what is the error? Let us assume that in kth layer, okay, as before, the sum of squared error E will define as half of, say, x j k, okay, that is the output that you get from the jth neuron in the kth layer, okay, minus d j, let us put k here also, that is the target output, okay, square of this, take the summation for j varying from 0 to m k. Okay. This is the number of nodes in the kth layer. Okay. Now, what is this x j k? This x j k is of this form. Okay. So, here in place of k plus 1, you have to put just k and accordingly modify all these expressions. Okay. So, that is what is my x j k, that is what I get from the jth neuron in the kth layer. Okay. So, to apply my training algorithm following the gradient descent procedure, I have to take the derivative of this with respect to w I j k. Okay. So, what I have to find out is, I have to take del E del w I j k. Okay. What will be this? Again, following the similar derivative approach, this will be simply x j k minus d j k, okay, into del of x j k upon del of w I j k. Now, here you find that why I am putting this del of x j k, del of w I j k, which I did not put in case of single layer. The reason is, this x j k is again an weighted sum of the outputs from the neurons from k minus first layer. Okay. And the outputs of the k minus first layer are actually weighted by the corresponding w I j k. Okay. So, I have to do this, and not only that, this x j k is now a nonlinear function of the weighted sum of the outputs of the k plus first layer neurons. Okay. So, when I take this gradient has to take care of that nonlinearity as well, right. So, when I compute this, as I said earlier, that the nonlinearity that I have is of this form, R s is equal to 1 upon 1 plus e to the power minus s, and if I take the derivative of this with respect to W s, the derivative is like this. Okay. So, if I concentrate on this term, that is del of x j k upon del of W I j k. Okay. So, this will be nothing but del W I j k of the nonlinearity R of W I j k x I k minus 1, okay, where the summation will be for I is equal to 0 to m k minus 1. Is that okay? So, if I take this derivative, you will find that this will be nothing but x j k, okay, into 1 minus x j k coming from this particular expression, okay, times x I k minus 1. Is that okay? So, if I put this in this expression, what I get is del E del W I j k, that will be simply x j k minus d j k, okay, into x j k into 1 minus x j k into x I k minus 1. Okay. So, this will be the derivative of the error with respect to W I j k. Okay. So, naturally, when I go for the iterative algorithm, iterative training algorithm, I have to use this derivative for updation of the weight vectors, and this has to be done from layer to layer. Okay. In case of single layer output, it was only in one layer. Now, I have multi-layer output, I mean multi-layer perceptron. So, this weight updation has to be done from layer to layer. Okay. So, let us stop here today. We will continue this with this in the next class. Thank you.